afternoon, and welcome to the Smithsonian National Air and Space Museum. I am Jennifer Lavasser, a curator here in our Space History Department, and curator for a recent exhibit that we featured on spacewalking. I want to welcome all of you to our Moving Beyond Earth Gallery in today's What's New in Aerospace program, EVA Tools of the Trade. I also want to give thanks to our sponsors for the program today, Boeing, and also to NASA Television, who's broadcasting this program today. I also want to remind all of you at home that you'll be able to submit questions online, and hopefully our speakers will have some time at the end to answer those questions. And that goes out to all of you in the audience as well. We've been celebrating this early part of this year, the 50th anniversary of spacewalking, and the capability of spacewalking was very important for long-duration space exploration and developing living and working in space by humans. The space shuttle, retired a few years ago, had the incredible capability of taking humans to satellites and also constructing the space station. Of course, astronauts continue to maintain and operate the ISS today and do spacewalks to do that. But now we're looking at different capabilities and potentially using robots to service different satellites and do different operations instead of humans doing those things. Today's speakers will talk a little bit more about human servicing of satellites and have been intimately involved in that process over the course of their careers. And I will say they both join us today from the NASA Goddard Space Flight Center's Satellite Servicing Capabilities Office. First, I'll introduce Justin Cassidy on my far left. Justin is the Robotic Refueling Mission Deputy Project Manager. He was previously a systems engineer on Hubble Servicing Mission Tool Development at Goddard and will tell us more about developing those tools. And he's worked at NASA since 1988 and spent 15 years working on Hubble servicing missions. On my immediate left is Ed Rizak. He's the Robotics Facility Manager right now, but has worked in a number of different roles over the course of his many-year career at NASA, starting in 1976. Working on a variety of projects from spacesuit development to supporting life and microgravity research, and of course Hubble servicing, training astronauts and supporting those missions. So let's welcome them and get started with our program. Over to you, Justin.
Thank you. Good afternoon, everyone. Are we going to start the slideshow, please?
Yes.
Sounds great. So while the slideshow is loading up, folks, good afternoon again. I'm Justin Cassidy. What we want to show you today and in this gallery here are an experience of what is Hubble Space Telescope and what servicing Hubble Space Telescope means to us. We had developed a lot of customized tools, so both myself and Ed Rizak are going to go through a presentation. We're giving kind of a high-level overview and some details about what it took to be an astronaut and the tools that we created for these astronauts to make these servicing missions possible. So next slide, please. Great. Hubble Space Telescope. Everyone's heard about it. Size-wise, it's about the size of a school bus. There's reasons why we didn't paint it yellow like a school bus, because it lives in the vacuum of space. Space is cold. It's very dark. It's a vacuum. So it has thermal blankets on it, shiny blankets. And because of that, it has unique coverings on it. It makes it kind of a chromous kind of finish to it, if you will. Engineers designed Hubble to be serviced. There are unique features on Hubble, grapple fixtures, one up here, one over here, where the shuttle would rendezvous with HST, would reach out and would grapple one of those fixtures, as you see right here in this picture, and it would bring it into the cargo bay, where it would dock onto a unique fixture in the back of the shuttle in order to bring it in and latch and mechanically and electrically mate to the shuttle. From there, that became the platform for astronauts to perform their servicing. The docking ring that it attached to was kind of like a lazy Susan. They were able to turn it around so the astronauts had the ease of accessing the front side, one side of the telescope, while being on the remote manipulator system as they performed their servicing activities. Now, because Hubble was supposed to be serviced by astronauts, they added features onto the Hubble Space Telescope, and these are foot restraints. A foot restraint was in place because an astronaut is floating around in space. They needed a means of tying themselves to structure, and they would do that with a foot restraint. And there's one right over here, over in this display case, one of these typical foot restraints. Also, handrails, they are floating around, so they had to move around the telescope hand over hand. And because of that, we put a lot of linear feet of handrails. We colored them yellow, which easily for them to see as they translated around Hubble Space Telescope doing the servicing. Common interface. Hubble was meant to be serviced. We knew over time, because it was a modular spacecraft, that instruments in different boxes that over time would fail, they could be changed out. So we made all the interfaces, mostly all the interfaces, a 7/16 bolt. And we have a couple examples here today. As far as the odometer of Hubble, Hubble's been up orbiting, doing great work for us for the last 25 years, racking up over 135,000 orbits and 3.7 billion miles. Next slide, please. So Hubble was designed in the 70s, but not launched until 1990. And back then, it was a state-of-the-art technology, but over time, things do become obsolete. So thanks to the on-orbit servicing, we were able to maintain Hubble to keep it operating at its peak scientific efficiency. For example, I wonder, anyone in this audience have a cell phone that's 10 years old? Is that even possible? Probably not. Okay, I have a flip phone in my pocket. That's pretty old. It's not really a slider or whatnot. It's not your slick smartphone. Does anyone have, or does anyone still have, their first telephone? This is my first telephone. I got it around 1990 when the Hubble Space Telescope launched. This was really cool technology. I had the ability to upgrade my cell phone by going to the cell phone store and getting a new phone. You can't do that with Hubble. Hubble was, the engineers who created it were very geniusly smart. Make it serviceable, make it modular, give it the ability over time to upgrade, keep up with technology by visiting it with astronauts over a course of 15 years, ending in 2009, all these different servicing missions, being able to upgrade these boxes to keep them operating. Even your cell phone camera. Hubble used to have very small cameras, they now have very large cameras. So Hubble was able to keep up with the times by changing technology, by being able to have astronauts visit it to perform servicing. Next slide, please. So here's kind of a summary of what the Hubble servicing missions were. From the launch in 1990 through SM1, 2, 3, 4, all of them performed different functions, doing different things. Now, the issue we had was these instruments got better and better. They also required more power. In order to require more power, we had to change the solar rays to something more efficient. So up here in SM3B, you see solar rays. Hubble's solar rays used to be very flexible, very good power cell generating capability, but they just weren't cutting it. We had to upgrade the solar cell to provide more power to these instruments that demanded more power, to become more efficient and help us to discover things in the future. Next slide, please. Here's a little chart that I kept to help me understand and track what was happening over the years. So in the left-hand column, what you would see would be basically all the deploy instruments. And OTA is the optical telescope assembly, focal plane structure, and they all have different position numbers. So over time, it gives the ability to track how long an instrument was in place, what was leaving, and what the new instrument was. So this is a snapshot of where we were when we started Hubble to where we are today with Hubble's fine instruments. Next slide, please. Ed, you want to walk us through the next few charts?
Sure. Hi, again, my name's Ed Rezac from Goddard Space Flight Center, just up the road. Yeah, the really neat thing about Hubble for me is she launched in April of 1990, had a life expectancy of what, 12 years, approximately 10 or 12 years. This year we're celebrating 25 years of on-orbit operations, and it's because we've been able to send women and men into space to service the telescope. And as a result, we've ended up with probably one of the most, arguably most important machine ever built by humans. Over that 25 years, I've got the red laser. Over the 25 years, we've taken more than 1 million exposures and have found over 22,000 new celestial objects. The greatest discoveries are because we've been able to go and upgrade those science instruments on board and repair them. Justin will get into the STIS and ACS repairs a little bit further on. Next slide, please. This is our STS-125 crew. This is the last human crew that visited the Space Telescope in May of 2009. We've had on board 2 teams of EVA, or extravehicular activity, spacewalkers teams. The first team was John Grunsfeld and Drew Foystel, and then the other pair were Mike Massimino and Mike Good. We had 2 mics out there at the same time, so this is Mass and this is Bueno. Training the astronauts is quite a challenge. You know, the project identifies the priorities for the servicing mission, and then we have to work with the folks at JSC, the Johnson Space Center, to choreograph and plan all those spacewalks. When the astronauts go out, they go out for approximately 6 hours at a time. So no motion, no translation, no maneuver is wasted. To train them to do that, we have a number of facilities, 2 big facilities, one right up here at the road, the Goddard Space Flight Center, and then the training facilities at the Johnson Space Flight Center. Excuse me. Oh, where'd my slide go? In planning for the Hubble servicing missions, one of the neat things we did, if you look at the 5 servicing missions, there was always a legacy. We always took a crew member from the previous servicing mission, so they had that corporate knowledge, brought it with them at the next visit. This was kind of a neat trip because we had not 1, but 2 and 3 returning Hubble huggers to the mission. Our commander was Scott Scooter Altman, pilot Ray J. Greg Johnson, and then Megan MacArthur was our engineer, RMS operator. The other 4 were the ones who suited up and went outside. When the astronauts go outside, it is truly a team effort because the folks inside are helping them with their procedures and reminding them what their next is. Now, for every hour that these fellows spent out walking in space or doing an EVA, we've trained them anywhere from 10 to 16 hours on Earth, depending on the complexity of the task. Next slide, please. I mentioned the facilities at the Johnson Space Flight Center. The NBL, or Neutral Buoyancy Lab, figured predominantly in a lot of our training. We train the astronauts, the spacewalking astronauts, in water because it's as close as we can get to training them to work in the microgravity environment of space while wearing a spacesuit and handling large pieces of hardware. The NBL is a large pool. There's 60.2 million gallons of water in this thing. It's 102 feet wide, 202 feet long, and 40 feet deep. The neat part about it is only 20 feet of that depth is below sea level. It's actually 20 feet above sea level. Any divers, scuba divers in the crowd? Okay. Scuba divers have to pay a lot of attention to how deep they go and how long they spend down there because of the effects on the human body. We didn't have to worry about that in the pool. Justin here was one of the divers and actually got into the water with the astronauts to train. The photos you see here is a representation of the Hubble Space Telescope, but not the entire telescope, because even though this pool is 40 foot deep, we would not be able to stand the telescope up completely because part of it would stick out of the water and our crew wouldn't be able to get to it. So we've cut the telescope in half, put the top half down on the floor of the pool, and then the aft shroud was situated in a mock-up representation of the payload bay of the space shuttle. Each crew member, my red laser just went out, each crew member
How about a green one, Ed?
I got to use the green one. Had support divers and safety divers assigned to them. In addition, while they're in the water, there is always a camera on that crew member for safety reasons. In the MBL, we use the opportunity, use the in-water opportunity, not only to practice, but to actually drive design for some of the tools you're going to hear Justin talk about. We bring concepts down to the crew, put them in the water with the astronauts. They evaluate it, they come back with ideas, likes and dislikes, and then Justin's team bring them back home and go over those comments with the engineers. And they do a very good job of turning those around with another revision of the tool for the astronauts to evaluate. Next slide. I mentioned the Goddard Space Flight Center. Wow. This is a photo of the world's largest clean room. It's at Goddard. It is currently occupied by the Webb Telescope team. But for a lot of years, the Hubble Development Project resided there. And my ash shroud disappeared. There it is. We have again, a high-fidelity mechanical simulator of the aft shroud of the telescope. Inside this aft shroud is where the 4 axial instruments are. They're about the size of a telephone booth, if anybody can remember telephone booths. We bring the crew up to Goddard and do training and procedure development there, as well as hardware design. Now, in this photo, you can see that most of the people are wearing white bunny hats, you call them. It's hard to pick out the crew in a crowd of engineers like this, so we have the crew wear blue hoodies so we can tell them apart. We spent a lot of time here at the High Fidelity Mechanical Simulator at Goddard, bringing the crew up. They're able to actually get into position. We used as much of the EMU, or the spacesuit, as we can, gloves, because that helps us determine reach and access. And they also learn what parts of the telescope they have to stay away from. John Grunsfeld, our payload commander for the last mission, in fact flew 3 Hubble servicing missions for us, reminded us constantly that the #1 rule of servicing the telescope was don't break the telescope. So the crew was able to become very, very familiar with what the telescope looked like, things that we could not represent in the MBL mock-up. Next slide, please. And Justin, is this where you're taking over?
Sounds great, Ed. Thanks.
Right. You're green, sir.
Okay, folks, over the many servicing missions we had, we brought tools. Some tools were easy tools, some tools were harder tools. But over time, because our change-outs of the equipment on Hubble became so complicated, we needed to develop more tools. So here's just a laundry list of all the different tools all through the servicing missions on what we had to fly up to space. Some we were able to reuse because sometimes one instrument had to replace with another, it's the same socket. So for example, this is one of the sockets that we would use to release one of the instruments. There's no reason building a new tool, we would just resend it. So that's what the column of, the line that reads reflown means. Next slide. The pistol grip tool. The pistol grip tool is basically your home power tool, but made for space. Space is very tough for a tool to work in. It's very cold, it's in a vacuum. Temperature swings are extremely great. So this is a very sophisticated computer-aided tool that allows us to do the right revolutions and as well provide the torque for all our different fasteners. Very important stuff. This tool was developed at Goddard and was used on all the servicing missions, and even today it's used up on space station for where it is used to support the EVA crew during their change-outs and maintenance work of ISS. Next slide. So here's a collection of all our sockets. Why do we need so many sockets? We have many different functions. They're all 7/16 bolts out at the front end of the nose here. So they're all socket tools to get on the 7/16. The end of the sockets wobble. For example, this is what we call a wobble socket. It bends. It's able to bend to comply and allow the astronaut to get onto the interface that you're turning. Other things, it extends if needed. So all these different tools have all those different functions. Some of them are smaller and rigid, and that allows us to get onto a shorter interface based on that requirement. So next slide, please. So Ed was mentioning the Hi-Fi Mechanical Simulator that is at Goddard. So the Hi-Fi Mechanical Simulator is just what we have here on the Hubble Space Telescope. It's the back end of the bus, if you will, the school bus. And that's where all the scientific instruments are stored. So they are either an axial instrument, something that looks like a phone booth, or it's kind of like a pizza pie shape. And so those are one of our instruments, as well as 3 of our fine guidance sensors. And this is what they look like on the bottom. The yellow represents the doors. There are only 3 sets of doors on the aft shroud to change out instruments, whereas the radial bay, or the pizza pie shape, there are 3 doors as well, and one of the instruments off to the side doesn't require a door. So if I want to get in here to change out an instrument, I have to go through 4 latches, and here are all the specifications for those 4 latches. Why does that mean something to us? Because we need to work with our tools. The tools need to be set to a certain value to allow us to release those bolts and allow us to get inside the door. It is very complicated and complex to do this. It became so complicated and complex, we actually made a door simulator that we sent down to Johnson Space Center so astronauts can practice closing these doors. These doors are very finicky. They got door gaskets, shear plates. It became an issue that we had to address to make sure that our crews were proficient and using their time most efficiently to learn to properly close the doors. Next slide, please. So what we're going to focus on today is Hubble Servicing Mission 4, and there are 5 EVA days. An EVA day is approximately 8 hours, let's say. So I want to focus on 2 of those EVAs, days 3 and 4. Those are important because they were doing something that we did not intend to do in the first place. The first one was easy, and that's install a cosmic origin spectrograph. So here is the aft shroud doors are open, and there is 1 empty bay there, and this is the instrument that was in that bay. And that instrument is called CoStar. And Jennifer, that is here in the museum.
It is.
So please take a look at that. This instrument was very important. When Hubble was first launched, there was an issue with the primary mirror. And this is the instrument that allowed to provide contact lenses in front of the other instruments to allow and correct for the aberration of the original mirror. So new instruments have that contact lens built into them. Therefore, CoStar became obsolete. We're able to remove that instrument. The new instrument that was going to go in its place is called the Cosmic Origin Spectrograph. The other 2 instruments are STIS and ACS, were installed on prior missions. These instruments failed. And the time that they failed, there was not enough time, resources, in order to create and build an entirely new instrument and then train the crew and then get the instruments up into space. There just was not enough time. So we were directed, fix them in space. So instead of doing box level change out, we decided to be surgeons, send the astronauts up there as surgeons, open up the box, pull the card out, and replace the failed component. And we did that both on the ACS instrument and the STIS instrument. And we're going to go in very detailed about what those took and the tools that it took to do those. Next slide, please. So here's the crew member here on the RMS. So not only did that RMS grapple Hubble and bring it into the shuttle bay, it also, you can attach a manipulator foot restraint. Jennifer, that's also here as well.
It is, yes.
So please take a look at that. This here attaches onto the RMS. The crew member puts their feet into there, and they are maneuvered around the cargo bay to assist the free floater, which is off here onto the side doing their task. So it's a 2-person task to do these change-outs. You've got a lot of hardware and tools associated on this stanchion along with the astronaut. So the astronaut does have a tool belt that they have their tools, but there's so much more that they're able to put it onto this tool stanchion, and that goes to their work site to assist them to make their job easier and faster. Next slide. So this is getting really, really into the details. The instrument that failed was STIS. STIS has an electronics box. It's called the main electronic box. So it's got 13 electrical cards in there. The electrical cards generate heat. It gets hot. So this is basically a big radiator plate. It radiated so much heat, there wasn't enough surface area, so they actually had to create an extension, like a diving board, in order to radiate more heat to make the instrument work more optimal. So because it was a diving board, they had to put this clamp up in the corner to cinch it down so during launch it would not disturb the instrument. Also, this is the card I want to remove. Gosh darn it, it's right behind this handrail. I need to take that handrail off. How can I change out the card if the handrail's in the way? So I have other obstacles around here. I think I could work pretty much around them. But I have to deal with this clamp, and I have to deal with this handrail. Next slide. This cover has got a lot of screws, and these screws also have washers. So this is a torque set fastener, number 4. There are 39 of these, and these are in your red zones. These are the ones that actually physically connect to each one of the 13 electronic cards. Even though we're removing one board, the entire cover has to come off, all the fasteners have to be released. Next up is the blue ones in these regions, and here is a socket head cap screw, and the larger ones on the right-hand side and the left-hand side are the number 8s. So when I add all these numbers up, just for the screws alone, it's 111 screws. When I add all the components up, that's 183 different individual components that I need to control. Now the problem is this change-out is occurring. This is a huge challenge in the aperture of an optical telescope. Any one little item that gets let loose could fly and float into the most worst place, and not only it would just disrupt science. So we had to be very concerned about controlling all this loose hardware. You can go to the next slide, please. So this is a very flat plate. There are no handholds features to grab a hold of. So we had to do a couple of things. We had to remove that little clamp in the corner, and this is the tool that we came up with. I also had to remove this handrail that was in the way, and I put on these devices called handrail removal tools, up and bottom. So I put these devices on them, I took the tool, I released the screws, and everything is captured, nothing would float away, and I'm able to put that into a garbage disposal bag, if you will. So now, how am I going to control these 111 screws that can become free-floating and ruin science for the future of Hubble? We created something called a fastener capture plate, a means of containing all these different fasteners. But how am I going to attach to something that is featureless? So what we decided to do is install these things called anchor guide studs. So out of the 111 fasteners, I'm going to take 4 fasteners, basically in 4 corners, and I'm going to put these anchor guide studs into the plate. And we're going to go to the next slide. So here's my challenge. So here's the electronic box, here's in light blue is the cover, and here are the floating fasteners that I need to control. It doesn't matter that they're floating around as long as I have control over them and they don't float away. So I need to put my fastener capture plate shield on top of these, making use of these guide studs. So let's go to the next slide. And I did that with this called the fastener capture plate. So I have blue arrows in the 4 corners indicating where I have pre-installed these anchor guide studs. I take this fastener capture plate, I put it onto the plate, I then cinch down the guide studs, and now this fastener capture plate is the 6th side to a box. I've now basically created a sealed compartment for releasing these fasteners to keep them under control. Next slide, please. So what you can't see underneath the window here is the pistol grip tool, and I have a pistol grip tool right here that we use in the pool. This is the workhorse, as I was saying, for the astronauts on space station and all the shuttle missions. This is a great tool. It can go 10, 20, and 60 RPM, so it's pretty fast, but it's a very strong tool in that it can break torque on fasteners and set torque. So it is a brute. It's a very strong tool. The problem is, when I'm doing 111 fasteners, it's really not fast enough for us. So we created this tool called the Mini Power Tool. The Mini Power Tool speed is 180, 3 times faster than the pistol grip tool. Now, just to give you an example of time, if I had 100 fasteners and I had to release each one of those fasteners 10 times, 100 fasteners, using the PGT, it would take me 18 minutes of time just releasing the fastener. And that's not including taking it out, putting it in, lining it up. So it would take us a very, very long time to release all those fasteners with this pistol grip tool. So that's why we created this Mini Power Tool. It's 3 times faster. And it doesn't have the torque because these screws are so small. So we didn't have the requirement for a very large, heavy torqued tool to use. Mini Power Tool. Next slide. So we also needed these different bits for the different type of screws that are installed on the fastener capture plate to release them. So we created these bits, and these bits are color-coded. It helped the astronaut identify which bit to use in order to release what screw. we arrange these also in what we call a bit caddy. So we equate this to the Indy pit crew, and the race car comes in, time's of the essence. We want that car turned around and right back out on the racetrack. Same thing for us with an astronaut. Time is at a premium. We want to make best use of astronaut time. How can we make this change out quicker? Even swapping one single bit onto the end of the mini power tool, whatever time we could save would be great. So we created this bit caddy where each one of these fasteners could be released by a bit. Next slide, please. So here's some crew evaluation / training, more like Ed was talking about at Goddard and down at JSC. Up in the right-hand corner is the mini power tool, and this is when we first decided to take something like the pistol grip tool and kind of divide it in half, a battery pack to a core to the main tool, which is very small. And that's myself with Mike Massimino, who was eventually going to do the sys repair in orbit. Down the left-hand corner, you see a couple of four yellow tools. So what we did is we traveled to Houston, we met up with a couple of astronauts, and we brought these 4 tools. Inside those tools, we preset them to a different speed. So we asked all the different astronauts, what do you think of this speed? So we're trying to find out what was the optimal speed, and that's how we eventually got to the number of 180. Up on the top is Mike Massimino with the pistol grip tool on the first version. This is the first time he ever saw the fastener capture plate before, releasing the screw. And this is before we decided to create the mini power tool. So eventually below, now you see Mike Massimino wearing some astronaut gloves with the mini power tool in a trainer that we delivered to his office to allow him to practice and train whenever he had time to practice and train. So this was a custom interface made for him as a training unit. Over on the right-hand side is a picture of one of the crew members using the pistol grip tool, releasing that yellow handrail that was in the way to remove the car. Why are we using that pistol grip tool? Because those bolts are really big and required more torque. And this is the actual tool I have here that you see right there. So this is our MBL training tool. Next slide, please. Okay, this should be a movie. So this is that MBL, and this is the crew member releasing a fastener. I'm sorry if it's a little dark. So he's lining the tool up, he's stabilizing himself. And there he goes to release it. So I apologize because this video is dark, but you got to remember, this is supposed to occur inside the aft shroud of the Hubble Space Telescope, which is like a photography darkroom. It is supposed to be dark. So the crew member brings lights on their helmets, and we also have a light up at the front end of the tool to allow them to light up the work site that they're trying to work on. So here's just a summary of stepwise of installing the fastener capture plate and how we used the mini power tool, very fast tool, with the bit caddy, optimally to change out bits quick and do the change out easier, and the crew member doing the different steps to release each one of the 111 fasteners. Next slide. I included this picture. This is what happens when I get to look at hardware that came back from space. So when the fastener capture plate came back, we took it off our hardware, it came back to Goddard. I opened up the box, and this is what I saw. I saw the fastener capture plate indeed capturing these small fasteners that Mike Massimino released. And you can see, here's the hole that the bit of the tool would go into to get onto the fastener, but the fastener head can't come back out the hole. So we were successful in capturing fasteners. Next slide, please. That clamp I was mentioning, that very small clamp that held the diving board of the little radiator. I just want to show you, here's a hand sketch I did back in 2006. It's something I thought would be a good idea for a clamp removal tool, something to grab onto it. And then you see here something that a concept or prototype that we're training in the pool, and then you see the flight unit. So it's not too far off from original concept of what this tool could look like from the start to the end. Down on the bottom is Mike Massimino removing the fastener capture plate. This was the first time at Goddard he actually removed it. And then here he is at training MBL removing it, as well as this is during flight, this is the fastener capture plate attached to the cover that was removed being translated to space. Now it's really hard to see, but there are little tiny wires on the back. Why? This is a radiator of an instrument. The thermal people have a thermocouple on the back of that. They want to know what the temperature was of that radiator during the operation of the instrument. So if we're removing the cover, the wire is still there. So we had to cut that wire. And if you go to the next slide, please. We use a wire cutter tool. It's basically a surgical tool that we made EVA friendly. We put a nice tip on the front with the cover to protect the astronaut from inadvertent actuations. There was a pinch point, so we put some banded cloth around here to prevent the astronaut from pinching his finger. And we put a little tether loop on the end so he could put a crew hook on it so the tool wouldn't float away from him. Next slide. And hit play. Oh, I'm sorry. Did we miss one? So this is on-orbit video of Mike Massimino releasing the fastener capture plate with the MEB cover. And you see a hand off the side here. This is Mike Good, Bueno, with the wire cutter tool reaching in and cutting that little tiny wire behind the plate. And if you can see, the little fasteners are floating around in their little pockets. Okay, next slide. So when it came to the cover being removed, we had to pull out that failed card. We had to use what we call a card extraction tool. And I have our MBL version here of this card extraction tool. If anyone has seen the movie Gravity, this tool and the wire cutter tool are used by Sandra Bullock in the movie. So this tool is famous. So we had to use a card extraction tool because the card is held in there, and this is what a typical electronic card looks like. It's not populated with electronic components, but this is basically the size of the electronic board that failed on STIS that we had to remove. Okay, next slide. Here is Mike Massimino removing the new card. The new card had its own brand new special ESD safe box to transfer and travel up into space. And when it was at its work site, he would remove it and then they would plug it back in to the instrument. And it is used in the insertion. So next slide. So when it came down to it, the bad card was removed, the new card was put back into its place. Now what do we do about a cover? We're not going to spend the time putting all 111 screws back into there. That's not how we work. We work to be very efficient, creating new ways and techniques to do things. So we created a new MEB cover that simply was put into place. A latch here and a latch here were swung outside, and we had these little tiny pins that you would lock in place, and it was fully installed. And we show the crew member down here practicing a glider with astronaut gloves, performing that task. So when Mike Massimino took about 35 minutes releasing all the fasteners just to take that cover off, this cover went on in mere seconds. Very efficient. Next slide. So now we're going to move quickly into another instrument, the ACS instrument. Here it is in the aft shroud. It also had an MEB box. That's where the failure of the card occurred. The problem is that instrument, ACS, as it sits inside the aft shroud of the Hubble Space Telescope, there's a big electronic cooler box right in the way. So there was just no way for us to physically access that box. The smart people figured out a way that, well, if I go into this box up here, which is this one right here, if I go into there, I could back power the instrument. They figured out a way for us to do it. So we had to go after a way of how are we going to get inside of this instrument? And more issues of more fasteners. So around the perimeter here are 16 fasteners with washers that you see cross-section right here. Underneath are 32 spacers. That's a lot of fasteners and components that we need to control. And then once that is done, we're trying to remove this black cover, 32 fasteners in all. So another big number thing to do. So we decided, well, let's not remove this whole thing. Let's just go right for the black cover. Let's go through this plate. And Ed provided me this cover right here. This is the exact replica of the cover that we had to go through. So it's pretty thin aluminum. So we devised a way to go through this instead of releasing all the hardware to get around it. Next slide, please. We wanted to install, just like STIS repair, anchor guide studs, a means of attaching devices that enable us to leverage a foundation off of. To do that, we wanted to remove 4 fasteners that were attaching, not all 16. And we did this with this particular screwdriver with a tip on it and a capture hook and a block. So once a fastener was released, it would be pressed into this block and no longer would be released and no longer could affect the telescope by flying into the places we don't want it to. So I have a video on the next slide, please. Okay, I don't. So here's a crew member removing one of 1, 2, 3, and 4 fasteners. And we can go right to the video and you're going to see the crew member training in the NBL pool. But first up, astronaut puts on his gloves. He grabs the tool. There we go. So now you see him releasing a couple of turns on the fastener. The fastener is released. He extends the fork. It captures behind the washer and gets the screw. He continues to back off the screw. There he goes. And the screw is released, and then would go back into the fastener capture block for retention. So once we had the 4 fasteners removed, 1, 2, 3, 4, we put these anchor guide studs. Just like STIS, ACS has its own anchor guide studs. So we created a caddy for these little guide studs to make sure that they were in a kit and all together and wouldn't float away. And then we had a handle to allow them to put these guide studs in. If we go to the next slide, we have a very short clip of the astronaut performing one of those installs. So he's screwing it in, he's releasing it, and it's installed. Very, very quick and easy. Next slide. So as far as the protective grid is concerned, here's a grid we needed to go through. So we developed something called a grid cutter, and that's what you see down here in the left-hand corner of the window. The grid cutter allowed us to install a device that basically became a guillotine for each one of the spokes of the frame. And because it had sharp edges, it had its own bag to go up in. So here's a crew member, John Grunsfeld, installing this plate, and then he uses the PGT. We need a PGT because we want high torque. It takes a lot of force to snap each one of those grids. So there's a PGT. And because of a strut right here, these fasteners couldn't be hit directly on, not even with a wobble socket. So we had to angle some of these screws towards the side. When it was done, we had a bag right here. So you're removing the grid that you cut and the tool, and it goes back into the same bag it flew up in, just like this flight bag right here. And then you've introduced a sharp edge. You have been able to control it and limit the amount of crew time they have into this exposure. Down here is a picture of that return tool and the grid that I saw and took this picture when the hardware came back down onto Earth. Next slide. Okay, so next up is the fastener extraction tool. I believe this is on display on the website, I believe.
Yes.
So if anyone has worked on anything in their home that involves a screw, and there are a number of screws, it's always that last screw that becomes really difficult. You're like, oh, I wish I knew that when I started. So what we decided to do is we're going to take these tools, and here you see the crew member in the pool doing the same. We're going to get onto each one of those little tiny 32 screws, and we're going to break the torque of every single one of them. Why? Because we want to make sure we can release every single one of them before we get more involved in the program. Another picture here is showing that strut I was talking to you about. The access to this box is really difficult. So we have 2 of these fastener tools, a long one and a short one. We're able to give the crew member the ability to choose a long or short based on where they were releasing these screws. When that was done, we have a ACS, a smaller version of the STIS fastener capture plate that did the same function. It allows us to capture fasteners so they don't float away and they don't ruin Hubble's optics. And then we see the mini power tool being able to reach through and releasing the screws. We can go to the next slide, please. Here's just a different view of the fastener capture plate just by itself. Here it has captured the black plate of ACS. Here it is without the black plate. And down here is a flight return picture. This is what I took when I found this. When I opened up the box, I saw the fasteners that it had indeed retained during the flight. Next slide. Okay, we can video. So here's a crew member in the dark aft shroud with that fastener extension tool releasing each one of those fasteners before you put the fastener capture plate on. And now with the fastener capture plate, even with the mini power tool being as small as it was, it still had problems being next to structure. So he would use the hand tool in order to get those really tough places. We'll let this play out. So this is back at Goddard with the mini power tool, releasing the different fasteners. So we're able to deliver to one of the astronauts, Mike Massimino, a STIS trainer in order for him to train. We couldn't do that for John Grunsfeld because we didn't, it would be a large structure in order to accommodate that training facility. So John Grunsfeld had to come up to Goddard often to perform his training activities, where Mike Massimino had to do it basically at his leisure in his office. So just like we had this card extraction tool that I showed you for pulling a card out, we need to do the same thing for ACS. With ACS, we're removing not one board, we're removing 4 boards. So we didn't want to fly 4 tools. So we decided to put the tool together. So we called it the indexing card extraction tool. And Ed, we thought we were really cool because we call it the iced tea. So the iced tea is right here. If you could go back one slide, please. Thanks. Here's the iced tea. And the iced tea had to attach somehow onto the ACS instrument. And if you recall, we put the anchor guide studs on before. The anchor guide studs, we had an adapter like a wishbone down here that would mechanically attach onto those guide studs. That gave us another foundation where the iced tea would then attach, as you see here, onto the box and allow us to index to each one of the extraction points to remove the card. When each card was removed, very, very sharp, didn't want the astronaut anywhere near it, we would then put it right immediately into a bag that would hold all 4 boards, and that's what you see right here.
Join a free highlights tour of the National
Next slide, please.
Aerospace Museum.
So when the ACS task was completed, it became easy to put things back together again.
Near the Independence Avenue entrance.
We've got a module, so since this cavity was the electron box cavity, we removed 4 boards, we had to put something back in. Remember, we're trying to back power the instrument. So we put the module back in here, and it goes into there. And you see the crew member, that's John Grunsfeld, in the pool performing the same activity. We then put another electronic box on the handrail, and then we run the harness all the way down to connect into the power supply. And by this, we were able to restore the instrument and power it back up. Next slide, please. So a couple of slides in conclusion. Here is the start of Hubble Space Telescope mission, STS-125 Atlantis on the launch pad. Next slide. Here is the beautiful launch that Ed and I got to witness firsthand. Next slide.
National Air and Space Museum. The 90-minute tour will begin.
The next slide shows HST docked into the cargo bay. You notice the rigid arrays on here. We have a cooling system here. This is one of the new instruments called Wide Field. And then you see the RMS over here in the distance. Next slide. We released Hubble. This is the release picture. A nice one of our pins commemorating the 25th anniversary of Hubble being in space, performing different operations for us. And lastly, next slide, we brought safely the STS-125 crew home, and we're able to share all the different experiences that our team experienced with the astronaut team and the servicing teams and the NBL teams and everyone together are a great opportunity to service the Hubble Space Telescope. Jennifer, that's the end of the presentation.
Great. Thank you so much. I think we're going to take some questions right now. If any of you have questions in the audience, feel free to step up to the microphone here. Marty is handling the mic for us. We may also have some questions from online.
We're going to start. Is my mic on? We're going to start with an online question. What are the possibilities for 3D printing tools in space, and what are the challenges?
Well, what are the challenges? So I'll tell you about 3D printing in space. Right now, there's a company that has provided to the International Space Station the printing capability. So the ability exists right now. I believe in the fall time frame, they're going to be delivering an upgraded printer with more capabilities. And both Ed and myself, we are now working on, not only before we worked on astronaut service, we're now working on robotic servicing. And there's a great robot up on Space Station named SPDM that we've sent some payloads up showing that a robot, just like an astronaut, can take things apart, and we'd like to also show we can put things together. And because of that, we have some requirements that are going to make use of 3D printing that our groups that we're partnering with to demonstrate that we can do in-space manufacturing and support not only IVA work, but also robotic work outside of space station.
Audience question, David.
During the servicing missions, what was your life like? Did you get any sleep?
Yeah, that's for you.
I'll take that. Yeah, sure, we got some sleep. Not as much as we could have used, but it's very hectic. You've got a deadline. You're working around a whole bunch of different schedules, including crew availability, the tool engineers responding to input to turn things around for the next evaluation. I got to tell you though, I think it's fair to say that nobody really complains because we are fortunate to be doing something that we're really enjoying and not a whole lot of people get an opportunity to do. And we're making history. So,
I mean, it's almost like the Super Bowl or the World Series for us. I mean, it's something we've been training and working with for
each
years.
day.
Okay, we have another online question. What was the most difficult Hubble servicing mission?
What? I'll tell you, difficult. I'll tell you which one was the most ambitious, and it's the one we've been talking about, the STS-125 mission. As we mentioned, Hubble is modular in design. You know, as technology catches up or parts wear out on orbit, you pull out one box and put in another. But in addition to that, we had two major instruments that had to be fixed on site. So it presented some challenges. Some of the tasks we thought would be more difficult turned out to be performed very, very smoothly, and then some ones we didn't expect threw in some surprises. But the neat thing about STS-125 is going into it, we knew that this was going to be our last opportunity to service the Hubble Space Telescope using a space shuttle. So we wanted to leave her in as best operating condition as we possibly could. And through the training, through developing of some awesome one-of-a-kind tools, we were able to do that. Every mission goes up with a list of priorities, a list of objectives, and then you've always got that back pocket wish list. We were able to get everything done on STS-125.
And the Hubble Space Telescope will continue to function, hopefully, with no failures for at least a few years to come, and return some great images for all of us to enjoy. I want to thank our speakers for joining us today, and for all of you in the audience here in the Moving Beyond Earth exhibition and also online on NASA TV as well, for participating and enjoying the show today. Let's thank our speakers, and hopefully you can join us next month for our next program.
Cool.